Welcome back to the Deep Dive. Today, we are looking at a world that really is the absolute pinnacle of engineering and, I guess, aesthetic ambition. We're talking about the construction of the modern superyacht.
We are. And if you follow this world, you've seen the designs. They're just incredible now.
Oh, they're unbelievable. You see these long flowing lines, these biomimetic curves. The superstructures look less like part of a ship and more like, I don't know, visionary architecture that happens to float.
And that incredible, completely unbridled digital vision, the one that's rendered on a $500 CAD system, it immediately slams into the centuries-old, completely unforgiving reality of the shipyard floor.
Right.
And that's our deep dive today. We're looking at a strategic analysis from a company called Blaupause Bootsbau, and they're focused on this digital transformation in the maritime world. They just perfectly articulate this central conflict.
Which is what exactly?
It's this massive, massive divergence between what we can design today and what we can actually physically build using traditional materials.
Exactly. We're in an era where, software can handle things like non-uniform rational B-splines in URBS, which basically lets a designer create literally any organic curve they can imagine. It's perfect.
It's perfect in the computer.
But then translating those perfect virtual surfaces into physical steel or aluminum plates, well, that's historically been an incredibly lossy process and an incredibly expensive one.
The complexity, the cost, the sheer time it takes for finishing, it essentially kills that perfect dream on its way to becoming reality.
So that's our mission today. We're going to dissect this huge strategic challenge, what the analysis calls the Gordian knot of high-end shipbuilding.
Right. We have to understand this dilemma between, achieving this modern design ambition, working with the very real physical constraints of metal, and then trying to overcome these previously prohibitive cost barriers of advanced composites.
And then we'll unpack the technology that promises to solve it. It's called Cast-In-Motion, or CIM.
And we'll show how it offers a verified digital manufacturing solution that really aims to resolve these technical and economic challenges.
Yeah.
The whole point is making these complex, precise designs fachlich correct.
And explain that term for us.
It means technically and economically correct. Not just possible, but correct from an engineering and a business standpoint.
Okay, so to understand the solution, we have to start with the problem. And that means going back to some foundational constraints that have, plagued metal shipbuilding since the late 19th century.
It's a long-standing problem.
The analysis calls this the geometric fetter, which sounds a bit philosophical, but you're saying it's just pure mathematics, isn't it?
It's pure, unforgiving geometry. I mean, here's the fundamental rule. Steel and aluminum show up at the shipyard as flat, rolled plates. That's it.
Flat sheets.
Flat sheets. And if you want to curve those plates and attach them to the internal skeleton of the ship, the frames, the stiffeners, without introducing enormous internal stresses or doing really intensive plastic deformation, the surface you're creating has to be, quote, developable.
Okay, let's get really clear on what developable means, because this seems to be the root of the entire problem.
A developable surface is one that can be unrolled and laid flat onto a plane without any stretching or tearing.
Like a piece of paper.
Exactly like a piece of paper. You can roll it into a cylinder, you can form it into a cone, but you can't make it into a sphere without crumpling it. Mathematically, it means the Gaussian curvature has to be exactly 0 at every single point on that surface.
And there has to be a straight line that lies within that curve.
Yes, the ruling line. If you can find a straight line that lies entirely within the surface at any point, it's developable. A cylinder has one, a cone has one.
So what shapes are ruled out by this constraint? What can't you build easily?
Well, anything truly organic, anything that's double curved, what designers call a free-form surface, a sphere, a shape like a potato, any complex biomimetic curve. You just can't make those from flat plates without forcing the metal to stretch and deform in two directions at the same time.
And that's hard to do.
It's incredibly difficult and expensive to do it uniformly. So designers are forced into these aesthetic compromises right from the start.
So that explains why you see so many superstructures that look kind of segmented or angular or faceted, even on these yachts that cost hundreds of millions of dollars.
Yes, they are sacrificing the pure aesthetic for basic manufacturability. They're giving up on those beautiful, flowing, double-curved forms that the owners actually want, because to get those shapes in metal requires these intense, specialized, and very high-risk procedures.
What kind of procedures are we talking about?
Well, you have to resort to techniques like the classic English wheel, which is a true craft. It relies on a specialized and, frankly, a vanishingly rare artisan to hammer and stretch the metal into shape by hand. Or you use something called thermal line heating, where you use very strategic heating and cooling to induce a controlled distortion in the plate. But all of these methods are incredibly time-intensive, they're high risk, and they build significant internal stresses into the material itself just to get the basic form. The geometric fetter forces compromise before you even stripe a single welding arc.
Okay, so even if you manage to wrestle the metal into that initial shape, the moment you apply heat to join those plates together, the problem just gets worse. It becomes physical.
Now you enter the realm of what the industry calls the hungry horse effect.
The hungry horse effect. It's a great name. What is it?
It's the aesthetic nightmare that's induced by thermal warp during welding. So think about it. When you join two metal plates, you're using either aluminum welding, which is around 600 degrees Celsius, or steel, which is up to 1500 degrees.
That's an immense amount of localized heat.
Immense! You're concentrating all that energy in a very small area. The material expands, and then as it cools, it naturally tries to shrink.
But the plate is already fixed in place on the ship's frame, isn't it? It can't just shrink freely.
It absolutely cannot. It's fixed to the internal structure. The outer skin, the plate, is welded to this rigid internal skeleton of frames and stringers. So when that weld cools and the metal tries to shrink back, the frame holds it in place.
So stress builds up.
Enormous tensile stress builds up in the plane of the plate. And when that stress exceeds the material's critical buckling strength, the plate just gives way.
And it buckles inward, right? It collapses between the support ribs of the frame.
Precisely. The external surface caves in between those rigid internal frames, which makes the underlying structure visible from the outside. It literally looks like the ribs sticking out of an emaciated, starved horse.
Now, I can see how on a commercial ship, like a massive oil tanker, maybe you can live with that if the structural integrity is okay.
Yeah.
But for a superyacht, where the surface is the ultimate expression of perfection and luxury, that sounds like an absolute disaster.
It is an absolute exclusion criterion. There's no debate. When you have a high-gloss, multi-layer paint job that costs millions of dollars, the light reflection on that surface has to be flawless, like a mirror.
Any disruption would be immediately visible.
Any disruption, any visible ribbing from the hungry horse effect is completely unacceptable. So this physical flaw, which is just inherent to applying heat to thin, supported metal plates, forces the entire industry into this disastrous economic cycle.
And that cycle is the reliance on manual fairing. This is what Blaupause calls the economic time bomb. This is where that initial, supposedly low cost of metal just explodes.
Right, absolutely explodes. The traditional solution is a process called fairing. It means applying these thick, epoxy-based fillers, sanding them back, checking the surface, and then repeating that process, sometimes dozens of times until the surface looks optically fair.
And this process had some really severe consequences.
3 of them, and they're all terrible.
Let's start with the one that affects the yacht's actual performance. Parasitic mass.
The weight gain is just staggering. The analysis reports that to smooth out all that distortion, to hide the segmentation from the geometric fetter and the hungry horse effect, you might have to apply epoxy filler up to 10 centimeters thick in some extreme areas.
10 centimeters, that's almost 4 inches.
In extreme cases, yes. It is not at all unusual for a large superyacht to be carrying tons of this epoxy filler. And this mass is entirely parasitic. It adds 0 structural strength.
But it does add weight.
It adds a lot of weight. It increases the ship's draft. It significantly increases hydrodynamic resistance. And ultimately, that reduces your speed, your range, and your fuel efficiency. You are literally sabotaging the yacht's performance on day one, before it even touches the water.
So they're burying the design flaws and the physical flaws under tons of inert, useless weight. That leads straight into the second consequence, which is the cost explosion.
The labor costs are just brutal. Fairing and what's called longboarding, where they use these long manual sanding boards to check the optical fairness of the surface, it demands thousands and thousands of man-hours from highly specialized surface technicians.
And these are skilled workers.
Highly skilled and increasingly rare. An industry manager quoted in the research said, often, finishing is 70% preparation fairing, sanding. This is frequently the single most expensive stage of the entire yacht construction, and it relies on a workforce that is aging and is critically scarce worldwide.
I can imagine that makes it a huge risk factor for any project budget.
A massive financial risk. The final cost block is completely variable. It depends entirely on how well the welders perform their job. A little more thermal warp from the welding team means the bill for the fairing team just skyrockets.
I read this one account where a shipyard owner apparently kept a sample of a thick, failed piece of fairing on his desk, just as a reminder of how much wasted material and labor was going into every single hull. Is that really the industry reality?
It's the brutal and often hidden reality. That cost, that risk, that wasted material, it all traces directly back to the fundamental geometric and thermal constraints of working with metal. But there's a third and equally disastrous consequence.
And that's the long-term quality risk.
The structural incompatibility of the materials you're using.
Right.
We're talking about the maintenance and quality risk. Metal and epoxy polymer have profoundly different coefficients of thermal expansion. CTE.
Meaning they expand and contract at different rates with temperature changes.
Exactly. So when a yacht experiences temperature cycling, say moving from a cool dry dock in northern Europe to the blazing hot sun of the Caribbean, the metal hull expands and contracts at a very different rate than the thick polymer filler that's slathered on top of it.
And that would create stress at the boundary between them.
Massive shear stresses right at the interface. And eventually, the more brittle epoxy develops microcracks. Water gets in. That leads to corrosion happening underneath the filler, and ultimately you get catastrophic paint flaking, which then leads to these multi-million-dollar refits and huge reputation damage for the shipyard. You're basically creating a time bomb just to fix a short-term aesthetic problem.
Okay, so metal is clearly a physical and economic nightmare if you're trying to achieve these complex, high-gloss surfaces. So the logical technical solution would seem to be composites, carbon fiber, glass fiber reinforced polymer.
GRP or GFRP, yes.
They offer superior strength to weight, zero corrosion, and crucially, they allow for any organic form. They completely eliminate that geometric fetter and the hungry horse effect.
Composites are, theoretically, the perfect answer, but they failed to conquer the large custom superyacht market for one simple, purely economic reason, which Blaupause identifies as the plug-and-mold problem.
Okay, walk us through that. Why have composites been so difficult for one-offs?
To create any composite part, you first need a negative form of mold. And traditionally, to create that mold, you first need to build a positive model of the part, what the industry calls the plug.
And this plug has to be perfect.
Absolutely, 100% perfect. Because any flaw in the plug gets transferred directly to the mold, and then that flaw gets transferred to every single part that you make from that mold.
And that's where the economics of scale just completely break down for unique vessels, right? For a one-off project.
That's the entire issue. Tooling costs for composites only really make sense. They only amortize over large production series. If you build 100 identical boat hulls from one mold, the cost per unit for that tooling is low.
But a superyacht isn't a production boat.
No, superyacht construction operates under what the analysis calls the unicat reality. It's a unique piece. If a yard needs a custom radar mast or a complex stern section or a unique bow, that specific form, that tool, is only ever going to be used once.
And the cost to build that one-off tool is just too high.
It's so high that it forces them right back to the suboptimal, but what appears to be initially cheaper, metal construction.
To really appreciate the scale of this economic barrier, let's detail the traditional process for creating that plug and mold. The analysis calls it the 19-step nightmare.
And that is not an exaggeration. It's a manually intensive, almost archaic process that can often take months. It ties up massive amounts of shipyard space, material, and highly skilled labor. We can break those 19 steps down into about 5 main painful stages.
Okay, what's stage 1?
Stage 1, plug construction. This starts with a giant block of material.
You're not kidding.
You literally glue massive blocks of foam polyurethane or polystyrol onto a supporting frame structure. Then this enormous block is sent to a large-scale CNC milling machine to be machined into the general shape of the part.
So even at this very first stage, you've created a huge amount of material waste just to get a rough, positive shape.
A mountain of foam dust. And then the endless manual labor begins.
Which is stage 2.
Stage 2, surface finish of the plug. The milled foam is rough, it's porous, it's covered in cutter marks from the CNC. So it has to be manually filled with paste, sealed, sanded, varnished, polished, and then waxed, all to achieve a perfect mirror-like finish.
This sounds incredibly labor-intensive.
This is the most critical stage. It demands hundreds of hours of manual labor by highly specialized model builders. If they miss a single microscopic flaw, a tiny pinhole, it gets transferred to the mold. It's a huge point of failure.
So once that plug is finally perfected, which might take weeks, you then move to actually making the mold.
That's stage 3, molding. You apply a release agent to that perfect plug, and then you start manually laminating the actual negative mold onto it. You're applying a special tooling gel coat, then layers of glass fibers and resin, building up the mold wall layer by layer by hand.
And that mold is structurally weak at first, I imagined, so you have to reinforce it.
Massively. That's stage 4, reinforcement. To prevent the mold from warping, either from the exothermic curing stresses of the resin or just from being moved around the shipyard, you have to build and attach these massive steel or wooden structures to the back of it. They often look like a giant egg crate.
Which just ties up even more material, space, and time.
Correct. And then finally, after all that, you get to demolding.
Stage 5.
Stage 5. Demolding and finish. You have to separate the heavy, reinforced negative mold from the plug. This is often a pretty brutal mechanical separation process. You're using wedges and compressed air.
And you risk damaging the very thing you spent months perfecting.
You frequently damage or even completely destroy the expensive plug. That positive shape that took all that time to perfect is now non-reusable special waste that you have to pay to dispose of. And the new mold itself then needs its own finishing and cleaning before its single intended use.
So this multi-month process is resource-intensive, it generates hazardous waste, and it relies on an endangered, expensive workforce, all for a single-use tool. That's the strategic blockade.
That is the blockade. It forces a yard to choose the suboptimal metal part simply because the cost of this 19-step nightmare for composites is just too high for a custom vessel.
We've established that the entire industrial bottleneck really rests on the necessity of that plug. So the great technological promise, therefore, must be to eliminate it.
Exactly.
And that brings us to the disruptive solution identified in the Blaupause analysis, Cast-In-Motion, or CIM technology.
CIM is the lever that cuts the Gordian knot. It completely redefines the tooling workflow. As you said, the traditional chain was digital data to a plug to a negative form to a part.
A long, expensive chain.
Very. By eliminating the plug, the new CIM chain is simply digital data directly to a negative form to a part. This elimination of the most complex, labor-intensive, and resource-heavy step, that is the core value proposition.
And this translates directly into radical efficiency. You're saying the multi-month, 19-step nightmare becomes a radically simplified 4-step workflow. The claim is an up to 80% time saving.
That's correct. It's a huge leap.
So how does that short workflow look?
It's digitally driven from start to finish. Step 1. Print and cast. The machine directly prints the form while simultaneously filling it with a casting resin. It happens at the same time.
Okay.
Step 2. Cure. You have a post-curing step, usually in a controlled environment or an oven, which is necessary to achieve the high formal stability you need for curing the final composite part inside it.
Step 3.
Step 3. Soak. The finished form is just immersed in plain water for automated removal of the printed outer shell.
And finally, finishing.
Step 4. Finish. The resulting mold is what we call near net shape. This means it requires only minimal sanding and polishing. We're talking about correcting microscopic flaws, not compensating for macrogeometric distortion.
Let's get deep into the mechanics here, because this isn't just a bigger standard 3D printer. It uses a hybrid architecture that's fundamentally different from traditional additive manufacturing.
Right. It's a synchronized two-head system, which is what makes it unique. Head number 1 uses something called gel dispensing printing, or GDP. This head extrudes a proprietary UV curing gel called Demengel. And because this material is highly viscous, almost like toothpaste, it can be printed very, very quickly, and it's cured instantly on the fly using UV LEDs. But crucially, this printed material only serves one function.
And what's that?
It creates a temporary, hollow, double-walled sacrificial shell. It's just a container.
So the shell is the high-speed geometric definer. It's acting as a very precise container for something else.
Exactly. That's what Head 2 does. While that shell is being rapidly built up layer by layer, an integrated casting head follows right behind it and intermittently pours a 2-component thermoset epoxy, a really durable plastic like Sikavirasin, into the hollow space between those printed walls.
So that's the brilliance of it. You're combining the speed of additive manufacturing to define the complex geometry with the structural quality of a cast thermoset core.
That's the hybrid paradigm. And this leads us to the key technical unique selling point of the technology: true isotropy.
Isotropy. Okay, this is a material science difference that is absolutely vital for tooling integrity, especially in the demanding maritime environment. Explain why standard 3D printing often fails here.
Well, traditional large-scale FDM or fused deposition modeling systems use thermoplastics. These materials are melted and extruded layer by layer, and those layers then fuse together physically as they cool.
Right.
The resulting bond between those layers, what we call the z-axis bond, is inherently weaker. It's often only 30% to 50% of the strength that you'd find within the layer itself. This is called anisotropy.
Anisotropy, meaning the mechanical properties vary depending on the direction of the stress.
Exactly. So an FDM form is structurally like a stack of pancakes that are weakly glued together. It's prone to splitting or delaminating right along those layer lines.
That's a huge problem for a tool.
It's a deal breaker. And they're often porous, which means they need extensive sealing to hold a vacuum during composite processes like vacuum infusion. CIM overcomes this completely because its core is cast from a thermoset epoxy.
And thermosets are different.
Fundamentally different. They undergo an irreversible chemical cross-linking, and crucially, the CIM casting process is wet on wet. This means the next batch of liquid resin is poured onto the still reactive underlying material. The polymer chains chemically bond across the pore intervals.
So you completely eliminate those weak layer lines.
You absolutely do. You're creating a continuous three-dimensional molecular network. The result is a monolithic, chemically linked block. And this means the strength and the stiffness are identical in all directions. That's true isotropy.
Which is non-negotiable for high-end tooling.
Non-negotiable. It eliminates the risk of z-axis delamination under the thermal or vacuum stresses that are inherent in composite manufacturing. This structural quality is what elevates CIM into the performance class of a cast or a machined metal tool.
Okay, but we have to address the thermal challenge. Composites need to be cured, sometimes at high temperatures, 80, 90, even 100 degrees Celsius, for prepreg systems. These massive polymer blocks are going to expand when they get hot.
They will.
So how does CIM manage the coefficient of thermal expansion, the CTE?
This is a major engineering point that absolutely must be managed to maintain those Fekelish correct dimensions. It's a great question. The Sikabyerson CIM 120 material, for instance, it uses an aluminum filler.
Aluminum powder mixed into the resin.
Yes. This aluminum powder helps manage the exothermia, that's the heat generated during the initial casting cure, and it also improves the thermal conductivity of the tool during use. However, the CTE for this material is still around 40 parts per million per Kelvin.
And how does that compare to metal?
Well, to put that in perspective, Invar steel, which is used for high-end aerospace tooling, is almost zero. And even a high-grade aluminum is only about 24 ppmk. So an uncompensated 10-meter polymer form that's heated to 90 degrees would expand significantly. It would completely warp the part being cured inside it.
That sounds like a massive precision failure just waiting to happen. So how do you ensure the form has the exact target dimensions at, say, 80 degrees Celsius?
The solution lies in the fact that the expansion is isotropic. It's uniform in all directions, which means it is predictable. And if it's predictable, you can compensate for it. The solution is software compensation, which is a core principle of design for additive manufacturing, or DFM. The CAD and the slicer software calculates the precise thermal behavior. If we know the target size is 10 meters at 80 degrees Celsius, and we know the material will expand by X amount between room temp and 80 degrees, the software simply prints the digital model smaller by that exact amount.
So you shrink the digital file, knowing that the physical material will expand into the perfect size once it reaches its target curing temperature.
That is exactly it. You are digitally compensating for a predictable physical reality. And this level of predictive compensation is only possible because CIM guarantees that isotropic material behavior. With anisotropic, layer-weakened FDM materials, reliable thermal compensation is practically impossible to achieve.
Okay, let's move to the final step, which sounds almost magical. Demolding. Instead of mechanically forcing a plug out of the mold and risking damage, what you call tooling trauma CIM uses water.
The soak and demold step is a major process simplification, and it's enabled by that outer shell material, the dimengal WB, which stands for water breakable.
Water breakable.
It's a very clever chemical engineering solution. The photopolymer shell is structurally stable when it's dry. It holds that epoxy core perfectly. However, when the form is fully immersed in simple tap water, the polymer structure begins to break down through hydration and hydrolysis.
And it essentially just dissolves away from the solid inner core.
It doesn't truly dissolve, it crumbles into these non-sticky flakes. And this passive, non-mechanical removal is the key. It completely eliminates the need for mechanical force that you have with traditional demolding.
So you eliminate the risk of tooling trauma.
Exactly. The surface damage that so often occurred when you were trying to extract a complicated plug just doesn't happen. Fine surface details, sharp edges, they're all perfectly preserved because the removal is entirely passive and gentle.
And thinking about the strategic implications, what does this passive removal mean for sustainability in the shipyard?
It's a significant shift toward what we could call clean manufacturing. You eliminate the generation of all that foam dust from plug milling. You get rid of the need for aggressive, toxic solvents that are often used in post-processing. The polymeric flakes that result from soaking can be filtered out, which allows the water to be reused. And the solid waste stream is much simpler and less hazardous than traditional waste, which reduces the regulatory overhead for waste management.
So we've established technical superiority and cleaner manufacturing. Now we have to connect this to the bottom line, because the entire argument here rests on proving that CIM makes composites economically superior to traditional metal for these custom one-off parts. This is the moment we dismantle the tooling trap paradox.
The tooling trap, it's the traditional fallacy that so many shipyards have operated under for decades. Metal is cheapest for bespoke parts because the initial tooling costs are low.
But it's a trap.
It is. It's a low entry cost that hides a catastrophic high exit cost. The initial cost advantage of building some simple metal jigs and support frames is completely, utterly overshadowed by the massive cost of fixing the inevitable imprecision of the final part later on.
And traditional composites, in contrast, had that massive front-loaded cost because of the 19-step nightmare of building the plug. CIM seems to strike the perfect balance between those two extremes.
That's the strategic leverage. By eliminating the plug, CIM reduces those initial tooling costs by up to 75% compared to traditional glass fiber reinforced polymer, or GRP, and that reduction brings the initial investment cost for a highly precise, perfect mold into the same financial ballpark as the simple, imprecise jigs you need for metal construction.
Let's quantify the most important saving then, the fairing crisis. We established earlier that for a 50-meter yacht, fairing can consume 10,000 to 20,000 man-hours. That's just an enormous financial risk tied directly to manual labor.
It's the single biggest cost block in many custom builds, and it's an exponential cost. You're repeating cycles of fill, sand, repeat, and the final bill is completely variable because it depends entirely on the initial quality of the welding.
Right. If the welders induced more thermal warp, the bill for the fairing labor just goes through the roof.
It skyrockets.
So how does CIM's technical advantage directly attack that cost block?
The near-net shape advantage is the financial killer of the old metal process. Since the CIM mold is printed with CNC-level precision directly from the digital CAD data, the composite part that comes out of it is geometrically accurate from the start.
So you're not compensating for the huge distortion from the hungry horse effect.
Not at all. You're only performing fine surface finishing. You're correcting microscopic layer lines or tiny pinholes. It's a different world of post-processing.
So we're not talking about marginal improvements here. What does the data actually show?
The fall studies and the analysis show that manual post-processing time can be reduced by up to 90%.
90%.
90. So think about the financial scale of that. If you reduce the necessary manual finishing for a large superstructure section from, say, 2,000 hours down to just 200 hours, and you're using a highly skilled labor rate of, let's say, 80 euros per hour, that's a direct labor cost saving of 144,000 euros on one single segment. That speed and precision completely changes project deadlines and profit margins.
Okay, we have a concrete, detailed TCO breakdown for a specific component. A complex, organically shaped custom radar mast about 4 meters tall. This case study seems to perfectly illustrate the trap.
It truly does. The analysis compared the total cost of ownership for a welded aluminum mast versus a CIM composite mast. The final TCO for the welded aluminum mast came in at 45,500 mo.
Okay. And the CIM part?
The CIM composite part was a staggering 15,500 down.
Wow. That's a 62% total cost saving on just one custom component.
62%.
Let's break down that initial lie of the low entry cost. The initial tool cost for the simple aluminum jig was calculated at 2,500. The printed CIM form was higher at 8,000 euro. So aluminum starts with a 5,500 advantage. Where did it all go wrong?
It went wrong, as it always does in the fairing phase. That initial 5,500 euro advantage was completely obliterated by the manual labor required to fix the aluminum part.
Give me the numbers.
The welded aluminum mast required €4,000 in fairing material, so filler and sandpaper, and a brutal €24,000 in specialized fairing labor. That's 300 hours of longboarding.
300 hours. And for the CIM part?
The CIM composite part, because of its precision, required only 300 in material and €2,400 in fine finishing labor. That's 30 hours.
So the economic viability of the metal construction was absolutely destroyed by the single necessity of paying surface technicians to fix the physical flaws caused by the welding process. The low initial cost really was the tooling trap.
It proves unequivocally that for complex aesthetic surfaces, the break-even point for CIM is reached immediately, often on the very first part, because you eliminate that exponential, unpredictable cost associated with compensating for the imprecision of metal.
And beyond the direct financial savings, let's quickly touch on the critical strategic and ecological TCO implications. First, the weight savings.
Right. Eliminating tons of filler is a long-term economic win. Removing that parasitic mass improves the yacht's stability. It requires less power to maintain speed, and it reduces fuel consumption over the yacht's entire life cycle. That's a key consideration in modern life cycle cost planning.
And waste management.
Traditional fairing generates tons of toxic epoxy dust. That's special waste, Sondermüll, which is expensive to dispose of and requires highly restrictive health and safety protocols. CIM minimizes waste. It eliminates that massive foam plug waste stream, and the water-soluble shell simplifies the entire disposal process. It supports the shipyard's move toward cleaner manufacturing.
And finally, the workforce dynamic, the war for talent.
Automation via CIM directly tackles that. Fairing is notoriously physically stressful work. It's often described by the workers themselves as miserable high dust exposure, repetitive manual labor. Automation reduces the reliance on those scarce, physically stressed surface experts. CIM transforms this entire phase from a variable, high-risk manual labor job into a predictable, digitally managed process, which improves working conditions and the shipyard's competitive attractiveness.
Okay, so we have established that composite construction using CIM tooling is technically superior and economically viable for custom components, but there's a big hurdle. If a superyacht exceeds 500 gross tonnage, it enters the regulatory realm of SOLAS, the International Convention for the Safety of Life at Sea.
That's correct.
And this regulatory framework has historically been the final definitive barrier to using composites on a large scale, hasn't it?
It has. The entire historical fire safety dogma of large ship construction is based on one very simple axiom: steel does not burn. And this is codified in SOLAS Chapter 2.2, Rule 11, Structural Integrity.
And what does Rule 11 explicitly demand when it comes to materials?
It requires that the hull, the main structural bulkheads, the decks, and the superstructures must be made of steel or an equivalent material. And the definition of equivalent material is the regulatory hurdle.
What's the definition?
It must offer equivalent structural integrity during a fire, and critically, it must be demonstrably non-combustible.
And that's where organic composite materials just fail the test right off the bat.
Exactly. The FTP code, that's the fire test procedures, defines non-combustible as not burning or releasing flammable vapors when you heat it to approximately 750 degrees Celsius. Since the resin matrix of composites, the epoxy, the vinyl ester polymer, is inherently organic, it is combustible. It burns.
So standard FRP structures can't pass that test.
They cannot pass that prescriptive test, which de jure, by law, excludes them from major load-bearing roles on large SOLAS vessels. The traditional mindset is that a fire might burn out the contents of a steel room, but the structure itself holds long enough for evacuation.
So if the prescriptive rules say no composites, how in the world do we use this incredible CIM technology to build that lightweight, perfect composite superstructure?
We use the regulatory escape route, and it was introduced by the IMO back in 2002. SOLAS Rule 17, Alternative Design and Arrangements.
Rule 17.
This is the crucial shift. It moves away from a prescriptive rule set, one that tells you what materials to use, to a goal-based approach, which allows you to prove that your alternative design meets the safety goals, even with different materials.
Which means the burden of proof shifts entirely onto the shipyard and the naval architect.
Correct. Rule 17 allows you to deviate from prescriptive rules like Rule 11 if your alternative design, using composites for instance, can be proven through rigorous structured engineering analysis to offer an equivalent level of safety. It's a highly formalized four-phase process.
Okay, break down that necessary engineering analysis for us. What does the shipyard have to do?
First is the preliminary analysis. You have to clearly define your design deviation, the relevant fire scenarios you're designing against, like an engine room fire or an accommodation fire, and the specific safety goals, for example, maintain structural integrity for 60 minutes or allow safe evacuation within 30 minutes.
Then the real technical work begins.
Yes, phase 2 is the quantitative analysis. This is where you use sophisticated tools like computational fluid dynamics, CFD modeling to simulate heat and smoke spread, and you use finite element analysis, FEA, for structural simulation to prove that the risk level is acceptable.
Phase 3.
A comparative safety assessment. The results of all your modeling must be compared against a conventional steel vessel to prove that your proposed composite structure does not present a higher risk to life.
And finally, you have to get it all approved.
Phase 4, documentation and approval. All the data, your assumptions, your analysis, and your results have to be meticulously documented and submitted to the flag state and the relevant class society like DNV or Lloyd's Register for their official sign-off.
So the core conflict during a fire is this. Steel conducts heat very quickly, but it holds its structure for a long time. Composites are great insulators, but they can rapidly lose their structural integrity if the glass transition temperature, the TGO of the resin, is exceeded.
That's the fundamental divergence.
So how do the regulators manage that?
The IMO addressed this functionally. They created interim guidelines for use of fiber-reinforced plastic FRP elements. This framework accepts that safety can be achieved through a full system approach, not just by ticking a box that says material non-combustible.
So you can use FRP if you can prove the whole system is safe.
Exactly. It allows FRP if safety is achieved via a combination of factors.
Which I assume primarily means passive insulation and active firefighting systems.
That's exactly it. The composite structure has to be shielded by passive insulation, a thermal barrier, so that the temperature within the composite laminate itself remains below the critical TGO of the resin matrix, plus a safety margin for the whole duration of the required fire scenario.
And then you have sprinklers.
And you often have to mandate active systems like high-pressure water mist systems, things like high fog, which are specifically targeted to suppress the fire and reduce the thermal load on that composite material.
And to prove this whole system works, they need physical evidence, right? They often rely on large-scale testing.
Yes, large-scale functional safety validation is almost always necessary. The classic example is the ISO 9705 room corner test. You literally build a life-size section of the room or the deck house lined with your entire composite system, the laminate, the insulation, the paint, and you set it on fire.
Wow.
And you monitor the heat release rate and the smoke production rate. And this proves that the system works to prevent fire spread and limit toxic output, which is what enables the flag state to grant that Rule 17 approval.
So the regulatory landscape has adapted to allow for the technology. But for a shipyard to integrate a brand new digital manufacturing process like CIM, they need the technical validation of the class societies, don't they?
That's the final necessary step. And class societies like DNV and Lloyd's Register are actually very proactive in this space. They've developed specific standards for polymer additive manufacturing like DNBS TB203. They qualify the entire process chain.
So they're not just looking at the final part.
No, they establish an approval of manufacturable, or AOM status. This guarantees process stability and reproducibility from start to finish.
And this is where CIM's technical advantages become crucial certification enablers, right? They help you pass those tests.
They provide the necessary, reliable input data for the quantitative analysis required by Rule 17. First, material isotropy. Since the core is chemically cross-linked and cast, the material data, the tori, the density, the strength, it's all reliable and homogeneous. This is absolutely essential for the FEA and CFD modeling, ensuring the analysis is fachlich correct.
And what's the second advantage?
Digital traceability. The Massivit system, which is the platform for CIM, digitally logs every single step of the mold production. It creates an unbroken chain of custody. The class society requires this to ensure that if Form A was qualified, then Form B, which was produced weeks later, followed the exact same certified parameters.
So having precise, standardized material data and a complete digital paper trail, that eliminates the variability that regulators have traditionally distrusted in manual processes.
Precisely. The collaboration with suppliers like Sika means the specialized resins used in CIM come with precise published data sheets. This eliminates the variability you'd get from manually mixed pastes, and it provides the class societies with the reliable input data they need for certification.
Okay, so full composite structures are technically, economically, and now legally possible. But for a large shipyard, what is the most strategic, risk-minimized approach to incorporating CIM?
The current consensus in the industry is the hybrid construction approach, what some call the King's Road.
How-
You combine a traditional steel hull with composite superstructures. The steel hull handles the primary global loads, and it ensures that the fundamental SOLAS compliance is met without any complex deviation arguments. It's the safe bet.
And then the composite technology is deployed where it delivers the highest reward up in the superstructure.
Exactly. This strategy maximizes all the benefits while minimizing the regulatory risk. The key benefit is stability and weight. Composite superstructures are immensely lighter than metal.
And you want less weight up high.
You want as little weight as possible high up. Placing that weight saving there drastically lowers the ship's vertical center of gravity, which significantly improves stability and passenger comfort, and it allows naval architects the freedom to design higher decks without creating stability concerns. And on top of that, composites eliminate corrosion in those highly exposed upper areas, which reduces long-term maintenance costs.
And it enables the very designs that the owners are paying millions for in the first place.
It delivers the final aesthetic goal. The superstructures are the areas most demanding of aesthetic complexity. There's organic, double-curved surfaces. Using high-precision, CIM-derived tooling for these components is what enables those complex, flowing designs that would be either too costly or just technically impossible to execute in metal with the required level of surface perfection.
So let's bring this all home. We began with the historical failure of tradition, that geometric fetter and the hungry horse effect, which forced shipyards into this era of massive aesthetic compromise.
A compromise they had to bury under tons of filler.
Right. We uncovered the tooling trap paradox, which revealed that the true cost of metal construction was hidden in those tons of epoxy filler and the thousands of manual man-hours required just to compensate for physics.
And Cast-In-Motion cuts this knot. It does it by digitizing the entire tooling process and eliminating the plug. It delivers the speed and efficiency of digital manufacturing, reducing time by up to 80%, while maintaining the highest structural standards through its cast isotropic materials.
So this technology isn't just about saving time.
Not at all. It's an economic and a regulatory enabler. It provides the digital traceability and the reliable material data that are necessary to meet the demanding quantitative analysis requirements of SOLAS Rule 17.
So by embracing this hybrid strategy in CIM, the industry is moving from an era of compromise to an era of really unconstrained digital realization. The cost of complexity, which was once astronomical and completely variable, has been digitized and made predictable.
And that fundamentally changes the entire equation for naval architects. They are no longer restricted by the limitations of flat plate physics or the budget for specialized fairing labor. The crucial question for them now is not, can we afford to build this complex chase-in composite, but rather, if complexity is functionally free and we can guarantee a factually correct execution, how radical and innovative can we afford to make our next design? And that really is the end of compromise in luxury yacht building.